Hello, this is chapter 16. This is part of lecture 21. This won't be the entire lecture because I'm going to post this tonight. Normally we would have it tomorrow when we have class, but since we're not meeting tomorrow, this is just an introduction to this section. And as I said in class, we will cover it in more detail next week, but I wanted to give you enough background so that you can work on the homework over the weekend. And then if any questions that you have between now and when we meet again on Monday, hopefully will be answered here, or I can answer them then. So first thing I wanted to mention was moment of inertia. And I did I did mention it briefly in classes. This is the idea of moment of inertia. Now, this is the mass moment of inertia, which is similar to moment of inertia that you learn in statics. So if you imagine a blob rotating about an axis and you were to sum up all the little pieces of mass and multiply them by their distance squared from the axis and sum those up, you essentially would get your mass moment of inertia. Okay, so the equation speaks for itself. The mass moment of inertia is essentially r squared m, and different shapes will have different moments of inertia or mass moments of inertia, which I'll use the two terms interchangeably in this class because we're not going to be dealing with area moment of inertia. But for example, a thin rod is 1/12 ml squared. A circle is 1/2 mr squared. And so that there's a table in your book that you can look at as necessary. And then there's also this concept of the radius of gyration. So if you were to take all the mass and essentially concentrate it into a single infinitesimally small dot, then the radius of gyration would represent how far away from your axis of rotation you would need. And that would essentially give you the equivalent moment of inertia. So it's a concept that you should know. We will use it. Occasionally you'll be given the radius of gyration. And so from that, you can, if you know the mass, you can easily calculate I. And so I will come in handy when we're doing some motion problems with rigid bodies. And so this is represents in 2 dimensions. We will not really deal with moments of inertia or mass moments of inertia in multiple dimensions. But if you did have them, then you would obviously have to account for the change in y and z, just like you would if you're in statics. Although in statics we never really got into 3 dimensions either. So this is just a part of chapter 9. So I would review it, especially if you're going to take intermediate dynamics. But for now, we can just work. We'll just be using the equations that we have, and also we have to couple that with the parallel axis theorem. So as you recall, the parallel axis theorem says that if you're at a distance away from your center of your moment of inertia, then you need to add this extra term to it. So what I mean by that, actually I'll get to that when I show you an example. So the equation down here below shows the units, kilograms, meters squared, and then the units in customary pound, feet, second squared, just so you're aware of them. All right, so this is a conceptual problem. And so for this one, you can pause and think about it, and then I'll go and then start the video again, and then I'll say what the answer is. Oops, did something there. So the question was if we had 2 pendulums where we had one like that and one like this, where we call this L, this is L over 2, except this is 2M. So here's our pivot point up here, point O. So we have M2M but twice the length. The question is, which one has the greater moment of inertia? Or are they the same? So if we look at them, intuition says, well, maybe they're the same because you have twice the mass and half the distance. And the farther you are from the pivot point, means it's going to be more difficult to rotate, right? As per the parallaxis theorem. So remember that anytime we have I, we always have, for example, if we had a slender rod, it would be 112 ml squared, and that's just an equation that's right out of the book. But if you were, say, rotating this about a point other than its center of mass, then you would have to add to it an extra mr squared term. So just like the parallaxis theorem, if you remember that you had triangle, for example, and you wanted to rotate it about this point, this line down here, then you would basically draw a line from the centroid of the triangle, and we know that this would be 136 bh cubed from a static standpoint, and then we'd have to add to it this AD squared. So that's statics, but in dynamics, we use the mass. Anyway, getting back to this, we can see that if we know that I generically is just equal to the integral of r squared m. So m's a constant because it's mass, it's a point mass. And so if we rewrite this to be I equals mr squared, which is the general form of the equation, and then we were to go in here and look at this, well, for this one, what do we have? We have m times 2m times L over 2 squared. So that's so I equals what? It equals m L squared over 2. But if we look over at this one here, we have the same thing. We have m times L squared, right? Because if we just plug in L for our distance, then we just get ml squared. So this one obviously has the greater moment of inertia, twice of that. So for the same token, or the same, that's not the right word, but for the same idea, graph or the table, sorry, it's late. For the same, let me put this back to sharing so I can get to, sorry for the narration, it's been a long day. There we go. So here we have the two pendulums A and B with masses and lengths shown are released from rest. So previously it was this one, which one has the larger mass moment of inertia. So we determined it was B. But if we look at this one, which one has a larger angular acceleration immediately after release? So which one is it going to be? Well, you probably can infer that from what we've been talking about, because we know that for these, we know that the sum of the moments about O, which we're going to get to, is equal to I alpha. I know I haven't presented that yet, but hopefully you've done some reading ahead in the book. And so it makes sense that if the moment is going to be larger, and so if we look at A, and B, so going back to the screen, then A is going to have the larger angular acceleration. And that has to do with the fact that even though they have the same, they have essentially the same moment, but they have half the moment of inertia. All right. So that's the idea, is that the moment of inertia is in that equation I just showed you dominates. Now, kind of getting ahead of myself. So this question is probably better for later on when we've done a few more examples. But while we're still on this track, I want to, with moment of inertia, I want to show this example. Now, I did show this in a couple of the classes, so if you've already seen it, you can fast forward. But what this represents is the idea of if you have a moment of inertia and you're trying to calculate it for a composite body, which is the most I'm going to ask you in this class. is you will take a composite body and you will break it up into 2 or 3 or 4, however many components, just like you did before, where you have, say, in statics, you'd have a box with a quarter circle or maybe a circle. You may recall if you had the final last quarter, there was a P, essentially shaped like a P, and you had to find the moment inertia for that. But for this, we're going to use just this disc and this rod. So what we have is something that looks essentially like this. Now, what I've done is I've drawn the disc and the rod, and let me explain what this is. Hopefully it's not too out of focus. Light's not as good at night, but so what we have is this is a radius of 0.35. This is 1 meter from here to here. Okay, that's the 1 meter, like in the picture. Now we know the middle, this is y of the rod, it's 0.5. Okay, and so it's 0.5, the middle. And then if we look at the middle of this, respect to our datum, it's 1.35. Okay, so the first thing we want to figure out is where is the center of this? And you know how to do centroid. So there's the centroid. It's the sum of the masses times their respective y bars over the total mass. So if I do that, I get a y bar of about 0.84. So now I want to find the total moment of inertia for each piece. So in order to do that, I look first at the rod. Now I know the rod is 112 ml squared plus a mr plus an mr squared term. Okay, because this is the center of it, but I'm not at the center, so the composite center. So what I would then do is I'd say 1/12 of 12, because it weighs 12 kilograms, and then my length is 1, so 1 squared. So I get essentially 1, and then that's going to be plus 12 times r squared. Now what's r? R is the distance between here and here. So if this is 0.84, then, sorry, it's 0.84, then that distance is 0.34. So I'm just going to do 0.34 squared. And that should give me about 1.3872. All right, so that's that. And then we have I disk, which is 1/2 mr squared plus mr squared. And so for that, we have 1/2, 8, and then the radius, 0.35 squared. So that's the moment of mass moment of inertia of just the disk. And then its distance, which is 8, and then times distance, which from 1.35 to 0.84 is 0.51. So we square that, and we get this to be about 0.49, and this to be about 2.808. And so if we add everything together, the answer is about 4.96. All right. And again, what are the mass? It's kilogram meters squared. Okay. So that in of itself isn't terribly exciting, but then we can use that to do other things. All right. Let's go back. Now, the important part of this that I want to discuss is dealing with the equations of a rigid body. Now what they refer to is the idea that if you have a bunch of forces acting on something, and these are out of your book, and so again, it's something that you're going to want to read and review, but just to give you a quick overview of it, imagine you have a rigid body acting in space, and that's what these pictures show. And so maybe it's easier to draw it. Let me go ahead and stop sharing. So you have this blob in space, and you have all these forces acting on it. All right. And so let's say that's your center of gravity right there, G. So So as we know, if we have something like this, it's going to have a tendency to accelerate, right? So you're going to have, if I could say this is equal to ma, where the bar over the line of A means the acceleration of the center of gravity. So maybe the net of these forces causes this thing to move. But it also, we know, is going to cause it to rotate. And so another way to look at it is it's going to be, plus a rotation. So you have to account for it rotating in both cases about its center of gravity. So, but we know that if we look at our center of gravity, then as we learned before, we know that this is our translation. So this is just our sum of our forces equals ma. But if we add the moment or the rotation, then we know that the sum of the moments about g is equal to the change in our angular momentum, hg dot. So that's the rate of change of angular momentum, as we discussed earlier. So what we end up with really is this thing with all these forces acting on it is really equivalent, not really equivalent, but what they call equipolant, which is equal in effect, power, or significance. That's the definition. So equipolant. So for our purposes, you can pretty much say they're the same because the effect on the rigid body is the same in calculations. So we end up with this ma, plus we end up with the change in angular momentum. All right. So now, where do we get this change in angular momentum? And the slides talk about it also, but I'll just run through it right now. So recall that linear momentum is equal to mv. And so we know that you can also write it as r cross v if you have in 3D. But so we know that our angular momentum, hg, is equal to r cross v, and then times the change in mass. All right. So so where do we get that from? We got that from, we keep going, we have r cross omega cross r, since that is this. Okay. So angular momentum is really saying that if we take our linear momentum and it's the moment of momentum, and so if we sum all this up, we end up with hg, or which is effectively the angular momentum, not the change in angular momentum, but just the angular momentum. It's equal to this r cross omega cross r, or another way to look at it, and then of course times the mass, right? So you have this omega cross r, which represents velocity, and you have the r, which is the distance, giving it which gives it the moment of momentum, and then time delta m, or the change in mass. Now, we don't really have the delta m here represents if we had a whole bunch of particles. So we can really think of m as a constant. So if we think of m as a constant in another way, then what we end up with is the sum of all the particles, which is, again, taking a bunch of particles, putting them together. It all really, what it boils down to is the angular momentum about the center of gravity is, again, the moment of momentum. And so it's essentially the sum of the r squared m's, and then, but we pulled omega out because omega is a constant. And so really, so sorry, there's an equal sign there. So h about g equals omega times mr squared. So what is that? That's I. So in a sense, we have h angular momentum equals I bar times omega. And that's the important takeaway. Sorry, this is a little convoluted. And if we take the rate of change of that, then that's going to give us our I bar alpha. Okay. And then, so this is the rate of change of angular momentum. All right. Okay. The diagrams show this here, and you can take that, you can pause the video to read what this says. But here's the derivation, where it came from, and so what it appears like. And this, again, this is stuff I would expect that you guys can look at in the book. You don't need me to regurgitate it for you. I think the important thing is that we can describe general motion of a rigid body by replacing it by the sum of the translation and the centroidal rotation. So translation being ma and rotation being I alpha. That's an important takeaway with this. Now, when we look at our calculations, so far what we've said is that the sum of the moments, let me stop, equal to I alpha. But so let's look at this. Now, this is directly from page 1122 in your textbook. Now, so what we're showing is that normally if we had a cylindrical rod or whatever it is, we would, if this was the center G, and we were to say, try to calculate what was going on with it, it would just be the sum of the moments equals I alpha. And so that's the only thing you have. And so therefore, if you were to describe it doing the sum of the moments about G, then you'd have the moment, right, that's created minus Py, because that's the only force that makes a moment, times its distance, and that equals the entire I alpha. So by knowing what moment is on that and what force is P, then if you knew I, which would just be 1/12 ml squared, you could calculate the angular acceleration. Now, there's also another thing that we do where it's not always easy to take it right from the center. Oh, if you pick another point away from it, then you have to add this MAD parallel term. So what you're doing now is that when you sum the moments about P, which is no longer your center of gravity, it's still equal to I bar alpha, which is the rotation about the center. So remember, the I bar means it's at the center, the moment of inertia of the center piece, not somewhere else. Notice there's no mr squared term there, times its angular acceleration. But you add this MAD perpendicular. And the book talks about it very briefly. Could probably do a better job of describing it. But we'll do lots of examples so hopefully it'll square away in your head. So you can also write this as R cross MA also, if in 3D, which we won't really get too much into. Actually, in this class, we won't. So that's probably the biggest takeaway from what we would have done the first lecture two in section 16.1, is that if you're taking a moment about the center of gravity, it's just equal to I alpha. But if you're taking a moment about any other point, it's still I alpha about the center of gravity, but you have to add this MAD term. All right. So let's look at an example. And I may skip some of this and come back. So I'm going to skip that. Let's talk about this. And we'll do this example, and that should give you enough that you can start the homework and start working on it, and then I'll mop this up on Monday. So here we have a 60-pan panel sets on a rough surface, and so the surface here at A is rough. We assume B is smooth, and so we want to know how fast can we accelerate this truck without this panel falling backwards or just on the cusp of falling backwards. So when you see something like that, to avoid movement, then what do you know about B? Well, it's a smooth surface, there's no friction, but you also know that there's no normal force. So there's no normal force because it's on just about to move. So nothing's there. So that's important when we write our free body diagram. So if we look at, this is what our free body plus our mass acceleration looks like. We have our normal force B, normal force A, friction A, mg, all of that is equal to ma, right? The acceleration of air. Now, we don't have any angular rotation, so our I alpha term is going to be 0 in this case, but we do have mass times acceleration. So first thing we do is we want to figure out, what is our normal force A? So by inspection, we can see that's going to be 60 pounds. So if I sum the forces and the y to 0, I see that NA equals 60 pounds. All right. So then the next thing is, since alpha equals 0, normally we would do this. We would say sum of the moments about A equals I alpha plus MAD perpendicular. All right. And so what are the sum of the moments about A? So, well, the only moment at A, since this is 0, is mg times the distance. So the distance, this was 60 degrees, and this is 2.5, 2.5, right? So we know that for the distance here, that's half of the hypotenuse because it's the sine, it'd be basically the sine of 30 or the cosine of 60. So we know it's going to be 60 pounds, and we're going to say that this direction is positive, doesn't really matter. So 60 pounds times 2.5 cosine 60. So again, and we'll do more complicated examples, but we're accounting for all the moments. Remember, we want to know all the moments acting on this particle or this rigid body. And so that's really what this is, sum of the moments. So it's everything acting on it, force times distance. And then we know that's going to be equal to, now if it did have alpha, we would have to calculate the moment of inertia about this. But we wouldn't have to add an mr squared term because that's what this is for. So we would calculate the moment of inertia about the centroid, which would just what this would be, and then we'd add the alpha in there. But because it's 0, we write I alpha and just cross it out. But no, it's still in this equation. And then for our MAD, we know it's going to be plus our mass. So that's going to be 60 over 32.2 times the acceleration, and then times d perpendicular, right? So again, we're trying to find the maximum acceleration, so that's what we're solving for. So what's d perpendicular? So that's the perpendicular distance of MA. So what that means is if we look at, here's our point, and how far are we from it? That distance there, d perpendicular, because the force goes forever. So if we look at that, that's going to be times 2.5 sine 60, right? And so that's what gives us this distance. So that's important to remember. So the d perpendicular is always how, wherever that force is, what's its perpendicular distance to the point that we're dealing with. So as you can see, the math is pretty easy. The concept's a little different. And so it will take some practice. And, the thing is, I can't cover all of the theory in class and do examples. So I try to balance it out. So there is some responsibility for you guys to read this through, look at online resources and wrap your head around it. There's a ton of stuff out there. So if you're still struggling with the material and you didn't do that well in the midterm, then this is a kind of a wake-up call to say that you need to do more than just listen to my lecture. And I'd like to say that my lecture is the best thing ever and that by all that you could know everything, but that's far from it. It takes a lot of extra practice to understand this stuff. Okay, so we solve for acceleration and we get 18.59 feet per second squared. And then we want to know the second part is what is the friction coefficient? So that's pretty easy because then we just say sum of the forces in the x equals ma. And so for that, we know the only force is the friction force. So friction force at A equals 60 over 32.2 times our acceleration 18.59. So that gives me a value of about 34.6 pounds. So if that's 34, then I know my friction coefficient is just the ratio of FA to the normal force, which is 34.6 over 60, which is essentially about 0.58. All right. Okay, so I hope that helps, gives a little bit. It's obviously not the full amount from 16.1, but it should get you started. So have a good weekend, and I will see you guys on Monday. Thank you.